All right, I have a quick supplementary lecture for you. This is following up the in-class lecture on Leibniz and Newton on space and time. Leibniz and Newton are even better known than for this dispute about space and time. They are known as the co-creators of the calculus. And in this brief supplement, I want to connect their development of the calculus to the study of accelerated motion. So within the Aristotelian framework, math was revered, right? Remember, for Aristotle, geometry is the model of a place where there are successful scientific demonstrations. But it wouldn't have occurred to them that you could have a successful mathematics of messy things like unnatural terrestrial motion. It made sense to do math for motion in the heavens because that's perfect and constant motion. Right? Things there move in perfect circles at uniform speeds. Circles and uniform speeds are, as it were, made to be understood. Messy, changeable stuff is not necessarily thought to be amenable to mathematical treatment. Galileo, more than anybody else, but also Descartes with the development of analytic geometry and the ability to graph equations, really start to turn the tide. A mathematics of motion starts to be the central aspect of physics. In astronomy, you had descriptive mathematics, but here we're getting towards a kind of causal or explanatory theory of the motion of things that cause sensations in us. So by about 1650, Galileo has shown us that projectile motion can be described by a parabola. Descartes gives us the ability to graph motion with respect to time and lots of other relations as well. We have seen, via the work of Galileo and Descartes, that constant velocity motion is basically as easily understood as rest, right? The principle of Galilean relativity tells us that if we're in a ship moving at perfectly uniform speed and not changing direction, and we have the curtains closed to our cabin, there's no experiment we can perform to tell whether we're, scare quotes here, really at rest or really in motion. We'd want to specify whether we're talking about rest or motion with respect to a particular other object. So we've overturned the Aristotelian framework, and so rest is no longer more fundamental than unaccelerated motion. But accelerated motion is a different animal. We saw that with Newton and Leibniz on space and time, right? You can feel the effects of acceleration, Newton thinks, with respect to absolute space. And so we are now wanting to approach motion that constantly changes. That's crucial if we want to understand motion, right? Galileo was doing that with the constant acceleration of free fall. Ideally, we'd like to understand how fast a vehicle is traveling, not over the course of an afternoon, but at a moment. Right? If you're taking a carriage from Paris to Nice or something like that, it's not too hard to figure out the average speed, but that masks enormous variations in how the motion actually goes down. Sometimes the horses are resting and drinking water, sometimes they're at a full gallop, and so you know that a nice smooth line on a Cartesian coordinate system, which gives you the average speed, you can use the slope of that line to determine the average speed. That is a vast oversimplification of how motion actually goes down. But we know that in the real world, the rate of motion often constantly changes. That's what acceleration and deceleration are. Motion is itself change of position. Acceleration is the rate of change of that change in position. So it's a changing change of motion. And this befuddled mathematicians going back to the Greeks. Zeno has a well-known paradox according to which you cannot walk across a room because you first have to walk halfway across the room, and then you have to walk halfway across the remaining half, and then halfway across the remaining portion, and then halfway across the remaining portion, and halfway across the remaining portion. So Zeno, he didn't deny that you could walk across a room, but he has an argument that something that plainly happens should be impossible because it involves an infinite number of steps. Leibniz and Newton together developed calculus, which is the mathematical tool where actuality and infinity most closely come together. The real mathematics of infinity and different cardinalities of infinity and things like that get developed in the 19th century, so we're going to set that stuff aside. Galileo wrestled with these issues fairly squarely, trying to confront the issue of whether time is infinitely divisible. We saw Descartes arguing that space is infinitely divisible, but this leads to some paradoxes that really couldn't be solved prior to the work that Leibniz and Newton did. If space is infinitely divisible, then a 1-inch line segment contains just as many points as a 10-inch line segment does, because for every point on the 10-inch line segment, you can find a point on the 1-inch line segment. This gave people like Galileo a headache. It might well be giving you a headache. It can be solved, but only with mathematical tools that derive from calculus. What you need is the notion of convergence on a limit. So basically what Leibniz and Newton independently managed to do is think in terms of shortening and shortening and shortening the duration over which you are measuring average speed. Zeno puts an impediment in that path because he says in an instant there can be no motion, and so there can be no change of position, much less changing position, which is what acceleration is. So we know how to measure speed when it's constant, but how do we measure it when it's changing? To put it graphically, we know how to measure the slope of a line, but motion where the rate of acceleration is constantly changing involves much more complicated figures than a line. What Leibniz and Galileo show you to do is how to take the slope of that curve at any point. Zeno provides an impediment to that, saying there is no slope at a point. A point is too small to have a slope. But with calculus, you can solve Zeno's paradox. So if it takes 2 seconds to cross a room, then what you need is to cover half that distance in 1 second, and then another half of what remains, and another half. And so what it takes is 1 second plus 1/2 plus 1/4 plus 1/8. And so with calculus, you can show that as you get closer and closer, the distance to be covered gets smaller and smaller. This sequence converges not on infinity, as Zeno and successor mathematicians thought, converges on 2. And that's how you can show that Zeno's paradox is tameable. You can have infinitely small distances and durations, and yet integrate them into a mathematically clear conception of reality. So I want you to think about how well you understand this stuff and think about formulating some questions for me. The main takeaways from this part are how we need a physics of changing motion, not just uniform motion. Uniform motion is almost as easy to understand as rest. By the time of Leibniz and Newton, we start to be able to have a clear mathematical theory about rates of change of motion. That requires the mathematical tools of the calculus. From our standpoint, that's the final sort of ingredient that it's going to take to get a full Newtonian physics. That's what our next online lecture is going to be about. But you need to see how wrestling with the idea of the infinite and the actual, these philosophical questions, are crucial as we try to come clear about mathematical and physical questions. Thanks as always for your time and attention.